Imagine I give you a coin. It is not a fair coin. It lands heads 60% of the time and tails 40% of the time. I let you bet on it over and over again from a fixed bankroll of $10,000. You choose the size of every bet. How should you play it? Most people reach for aggression. If the edge is real, bet big. Some people say, bet everything. But repeated betting is not the same as a one-shot gamble. Once wealth compounds, sizing becomes the whole game. Now watch three traders face the same coin, the same edge, and the same realized sequence of outcomes over 200 flips. One uses half Kelly, one uses full Kelly, one goes all in. The Kelly trader grows dramatically. The half Kelly trader grows more slowly but stays durable. The all-in trader looks brilliant right up until the first bad loss, and then the process ends. That difference is the mathematics of compounding. In repeated favorable games, survival comes first, because one oversized loss can erase your ability to benefit from the edge at all. Kelly Criterion is the answer to that problem. Not what to buy, not whether an edge exists, but how much to risk once you believe the edge is there. To understand why Kelly works, you need to understand where it came from. It did not come from Wall Street or a casino pit. It came from Bell Labs in 1956. John Kelly was working inside the same research culture that produced the transistor and Claude Shannon's work on communication through noise. His paper was titled, A New Interpretation of Information Rate. The original problem was not how to bet on blackjack. It was how to transmit signals through a noisy channel as efficiently as possible. Kelly realized that the math had a second life. If a communication channel has noise, there is an optimal rate at which information can pass through it. If an investor faces uncertainty, there may also be an optimal rate at which wealth can compound through repeated bets. Shannon asked, how many bits per second can move through a wire with a given signal-to-noise ratio? Kelly asked the analogous question for capital. How fast can wealth grow when outcomes are noisy, but an edge exists? In both settings, the answer turns out to be logarithmic. That is the deep connection. Kelly Criterion is not gambling folklore dressed up as math. It is information theory translated into capital allocation. Most summaries hand you the Kelly formula and move on. But the derivation matters, because it tells you what the formula is actually optimizing. Suppose you repeat the same favorable bet many times, always risking a fraction f of your current bankroll. Wealth now evolves multiplicatively. After a win, you multiply by 1 plus b times f. After a loss, you multiply by 1 minus f. So after many bets, terminal wealth is initial wealth times the win factor raised to the number of wins, times the loss factor raised to the number of losses. That is why expected dollars is the wrong objective. A strategy can have positive expected value and still destroy wealth if it sizes too aggressively. Take the logarithm of terminal wealth, divide by the number of bets, and apply the law of large numbers. Wins converge to P, losses converge to Q. The long-run per-bet growth rate becomes PI log of 1 plus BF plus Q log of 1 minus F. Differentiate with respect to F, set the derivative to 0, and solve. The answer is F star equals BP minus Q, divided by B. That is the fraction that maximizes long-run geometric growth. Now plug in the simplest favorable game. The win probability is 0.60. The loss probability is 0.40. The odds are even money, so B equals 1. Kelly says the optimal fraction is 1 times 0.60 minus 0.40 divided by 1. That gives F star equal to 0.20. So even with a real 60-40 edge, the growth optimal answer is 20% of bankroll. At that fraction, the exact log growth rate is about positive 0.02013 per bet. That sounds small, but geometric edges compound relentlessly. Over 200 bets, the same $10,000 bankroll grows by a very large factor. Kelly is optimizing geometric mean growth, not expected dollars. This curve is the most important picture in the video. The horizontal axis is the fraction of bankroll you bet. The vertical axis is exact per bet log growth. If you bet nothing, growth is 0. As you begin to size up, growth rises because you are finally using the edge. But it does not rise forever. The curve peaks at full Kelly, then bends downward. Underbetting leaves some growth on the table, but the process stays robust. Full Kelly is the unique long-run optimum. Move past that peak, and the intuition breaks. More size does not mean more growth. It means less. Even though the game is still favorable, overbetting drags long-run growth down because losses compound more violently than gains. In this 60-40 even money example, a common shortcut says that 2 times Kelly gets you back to 0 growth. The exact formula is stricter. At 40%, growth is already slightly negative, about minus 0.00245 per bet. Push farther, and the curve sinks below 0. That is the ruin zone. Expected value can stay positive while compounding turns negative. In repeated betting, overbetting is mathematically self-destructive. A growth curve on paper is expectation, but nobody lives inside the expected path. Real investing means moving through one realized path drawn from a distribution of possibilities. So let us simulate 10,000 traders. They all face the same favorable coin, the same 60-40 edge, the same 150 trades, and the same $10,000 starting bankroll. The only thing that changes is position size. Start with half Kelly. Its median terminal bankroll is about $95,476. The 10th percentile is still around 19,173, and essentially none of those traders finish below $100. Now, move to full Kelly. The median jumps to about $204,980. So yes, the upside is stronger, but the ride gets rougher immediately. The 10th percentile drops to about $7,998. Then, look at 2 times. Kelly. This is where the visual should make you uncomfortable. The edge is still real. The coin is still favorable. But median terminal wealth collapses to about $6,928 below the starting bankroll, and about 18.1% finish functionally wiped out below $100. That is the asymmetry Kelly is warning you about. A positive edge is not enough. If the sizing is wrong, the distribution becomes toxic long before the thesis becomes false. Now, we get to the part that matters most in actual markets. Kelly assumes you know the edge. Traders almost never know the edge. They estimate it. Suppose the true win rate is only 52%, but your model tells you it is 60%. With even money odds, the true Kelly fraction is just 4%. But if you size off the mistaken estimate, you bet 20%. That is a 5 times overbet created entirely by parameter error. Not fraud, not bad intentions, just an overconfident estimate. This is the asymmetry professionals respect. If you underbet, you give up some growth, but the damage is limited. If you overbet, the penalty can be catastrophic because compounding works against you. The practical rule is simple. When the edge comes from noisy data, use half Kelly or less. The uncertainty in the input is itself a reason to size down. Fractional Kelly is the professional compromise. You deliberately size below the theoretical maximum because the cost of overestimating the edge is far worse than the cost of being a little too conservative. There is a famous rule of thumb that half Kelly gives roughly 75% of the growth with only 25% of the variance. The intuition is right, but it is not exact in every game. In this 60-40 even money example, the exact figure for half Kelly is about 74.7% of maximum growth, with variance near 25% of full Kelly. Quarter Kelly is slower, but more forgiving if your estimate of the edge is wrong. 3/4 Kelly gets you closer to the maximum, but demands more confidence. Beyond full Kelly, the trade-off changes sign. Variance explodes while growth deteriorates and can turn negative. That is why serious practitioners usually live below the mathematical maximum. Theory is one thing. The real-world stress test came from Ed Thorpe. Thorpe was an MIT mathematics professor who read Kelly's paper and immediately recognized its practical power. In 1962, he published Beat the Dealer, the first mathematically rigorous demonstration that blackjack could be beaten with card counting. What made the application so elegant is that the edge in blackjack is not fixed. It changes with the true count. When the count is poor, the player has no advantage, and Kelly says, "Do not bet." When the count turns strongly positive, the edge rises, and Kelly says, "Size up in proportion to that improvement." So the famous blackjack bet spread is not swagger, instinct, or table theatrics. It is Kelly Criterion translated directly into action. Minimum bet when the edge is weak. Bigger bet when the edge improves. That matters historically because Thorpe then carried the same logic into financial markets and helped pioneer quantitative investing. Kelly did not stay trapped in theory. It worked in casinos first, then proved useful in markets, which is why people still take it seriously. The single bet formula is only the beginning. The broader Kelly framework extends to multiple assets, continuous distributions, and real portfolios. Under log utility and Gaussian return assumptions, multi-asset Kelly takes on the same mathematical structure as the Markowitz tangency portfolio. In that setting, growth-optimal betting and modern portfolio theory are not rivals. They are closely related versions of the same optimization problem. That connection is easy to miss, but it matters. It means Kelly is not just a gambler's sizing trick. It plugs into the language of portfolio construction. In the one-asset continuous time version, the Kelly fraction becomes expected excess return divided by variance, mu over sigma squared. Here, mu means expected return above the risk-free rate, and sigma is annual volatility. If you plug in illustrative long-run U.S. equity inputs, roughly 7.5% excess return and 19.5% volatility, the formula gives a full Kelly fraction near 1.97. In plain English, that is almost 2 times exposure. Half Kelly lands close to 1 times exposure. And that is precisely why practitioners haircut the theoretical answer. The continuous time formula is elegant, but the leverage it suggests is often far more aggressive than most real investors can tolerate. Kelly Criterion is not a magic formula. It is the correct answer to a very specific mathematical question. How much should you bet when the edge is known with precision and the game is repeated under stable conditions? Real markets rarely hand you that clean setup. Fat tails can shatter Gaussian intuition and wipe out years of disciplined compounding in one violent event. Parameter error can make an apparently optimal position into a hidden overbet. Regime change matters too. An edge that worked in one environment may weaken or disappear in the next, while the model keeps sizing as if nothing changed. And even if the math were internally perfect, Kelly maximizes log wealth, not comfort, not smooth returns, not client retention, and not career survival. So the mature use of Kelly is not dogmatic. It is cautious. Use the framework to think clearly about sizing, stress test the assumptions, size fractionally, and treat the raw output as a ceiling, not a command. So the takeaway is simple. Kelly Criterion does not tell you what to buy. It tells you how much to commit once you believe you have found a real edge. The formula is compact. F star equals BP minus Q divided by B, bet in proportion to the edge. Respect the asymmetry of losses. Never confuse aggression with optimality. That is why Kelly keeps reappearing across gambling and investing. But in real markets, the theoretical answer usually has to be reduced. The world is noisier, fatter-tailed, and less stable than the model. So use Kelly as a framework for disciplined sizing, not as a license to maximize leverage. Next episode, Shannon's Demon, where rebalancing creates growth even in a zero-drift market.